Hello. What I'd like to talk about today is a calculus theorem about the limit of the products equaling the product of the limits. So let's go ahead and get started. And in this case, and I'm going to assume that you have a little bit of familiarity of the delta epsilon definition of the limit. And if you don't, well, I'll show you where it comes into play. Now, this is the idea. Suppose you have a function f, where the limit as x approaches a of f of x is big F, and the limit as x approaches a of little g is big G. So you have these two limits sitting here. And we would like to show and this is probably a guess of what the idea should be, that if I took a limit as x approached a of the product, we would like to show that's going to be the product of the limits like this. Now, you might say, why would we guess that? You can do some playing around, but I think it's somewhat intuitive. If little f is getting close to big F and little g is getting close to big G, you would imagine that the product would be getting close to the product, right? And of course, imagining it and proving it are two different things. So in order to show this, what we'd like to do is we would like to show that the difference, and I'm using absolute values here, that the difference between these two quantities is, we would like to show that this difference goes to 0 as x goes to a. So we would like to show that this limit here goes to 0 as x goes to a. That's what we'd like to show. So this means we're going to be examining this quantity here as we let x get very, very close to a. So how can we do this? How can we sort of nail it down? Now, this is a very, very common technique in mathematics where you're looking at this and you'd like to break this up somehow. So we could start, and you'll find that you do this a lot in calculus. You say, is there anything we can do inside these absolute value signs not to change the value of what's inside them? And one common thing, you can always multiply by 1, but I don't know of a good way of doing that. You can always also add 0. And the way you add 0 is you add and subtract the same thing. And notice little f is getting close to big F, and little g is getting close to big G. So you think about that, and you think, well, maybe I could subtract big F times little g of x. And since I'm subtracting this, I have to add the same thing. So it's clear that what's inside the absolute value signs here is equal to that because these are the same thing. Now, notice, you could have said, well, what about subtracting big G times little f and adding big G times little f? And that would work. That would also work. There's more than one way to approach these things. But this is one way that works. As an exercise, you could try to do it the other way. So you say, all right, these two are equal. Now, the next thing we do is when we're examining this, is we use the triangle inequality. And the triangle inequality says that the magnitude of A plus B is less than or equal to the magnitude of A plus the magnitude of B. So by the triangle inequality, this is going to play the role of our A, and this is going to play the role of the B. So this quantity here is now less than or equal to f of x, g of x, minus big F, g of x, plus big F of x, g of x, minus big F of x times big G of x. So by the triangle inequality, this quantity is less than or equal to this quantity. Now, using more algebra of absolute values, you notice that there's a G here, and notice that there's a big F here. So this part is actually equal to, I'm going to factor the absolute value of G out. And notice now we have f of x minus big F of x, minus big F, plus, let's factor the big F out. And then we have little g minus big G. Okay? So this quantity here is less than or equal to this. Now, this is where the intuition comes in, and where you're going to have some choices to make. Now, we know, and I'll go ahead and write this down. This is technically not part of the proof, but this is part of thinking about the proof. We know that little f is getting close to big F. We know that little g is getting close to big G. So that means this is going to be getting small. This is going to be getting small. This is going to be getting close to big G. And that is already big F. Okay. So the seasoned mathematician would say, okay, arbitrarily small times finite plus arbitrarily small times finite is arbitrarily small. And that's a calculus that a more seasoned mathematician would use. However, this video is not, seasoned mathematicians don't need this video. So we're going to have to somehow nail that down. So what do we do? Well, we'd like to find a bound for this G. This is a constant, so we don't really need to bound that. We'd like to find a constant here, this G. And we'd like to find, we know this is going to get small, but we'd like to know how small. And somehow it would be great if somehow this whole thing down here, we'd like to, after all is said and done, we'd like for that to be less than some arbitrary epsilon over 2. And we'd like for this to be less than some epsilon over 2. So this is one way to do this. We'd like to find something here that's going to multiplicatively cancel this. And so this is what we can do. So the first thing, because G is going to big G, we can say that for any, let's call this epsilon sub G, there is some, let's call this delta 1, where the difference now between G of x minus G is going to be less than epsilon G. And now let's just be clever about this epsilon G, because it says any epsilon G. We can do this. So one thing we can say is we want this to somehow cancel this value here. So what I'm going to say, because I want this to work out the correct way, and I want this to work out the correct way, I'm going to let this epsilon g here be less than the minimum. And I'm going to just arbitrarily pick the number 1, but you can pick any finite number here you want. And then I'm going to say this will be some epsilon. There's your epsilon over 2. But I want to somehow make this, cancel this f out by some means. So I'm going to write this as the absolute value of f plus 1. Okay? And then that's for delta 1. Then there is some, let's say, delta 2, where for, and let me be better here. For that, in other words, for x minus a, for x being within delta 2 over a here, we know that the f of x minus f is going to be less than some epsilon, let's call it f. And I'll go ahead and say that's going to be the minimum of 1, epsilon 2, and we're going to want to divide out by this g here. So I'm going to call this big G plus 1. Absolute value of G plus 1. Okay, there's your delta 2. And then I'm going to let delta be the minimum of those two deltas. Delta 2, delta 1. Got the order wrong, but it still works. So now what happens? Well, we got this. Now remember, this delta is smaller than those two deltas there. Then we know that we have this absolute value G. This part right here, this f of x minus big F. Well, then we're going to write this as epsilon over 2 times big G plus 1 plus F, absolute F. Then that's going to be your epsilon over 2. And remember, we pick this thing right here because we want this to somehow cancel this F. And again, there's no, this 1 here, just make it some positive number that's smallish. Okay. Now, what we want to do is we now realize that because this is getting smaller than G, this is now, this part right here, because remember, as x approaches a, g of x approaches big G. Well, this thing right here, well, we can say that the difference between, well, this thing here is going to be less than or equal to this limit of G, because remember, this is getting plus G plus 1. Then we have this epsilon to absolute G plus 1, right? Because remember, this is getting very close to G. So this part here is also true. then we have this. And we got these absolute values like so. Now, the cool thing about this, because remember this one is, well, it's going to be bigger than this difference here. Well, take a look at what happens. This cancels. And this part here, so you notice this denominator here, and I forgot the absolute values here. That's going to be less than or equal to 1. So what happens, this cancels. So this is going to be less than epsilon over 2 plus with this bound right here for this part being smaller than that part, that's epsilon over 2, which is epsilon. So what we see here, remember our chain of equalities or inequalities, this part is bigger than that, greater than or equal to this, which is greater than or equal to this, which is greater than or equal to this, which is the same as this right here. So we see, so the conclusion is, as, I should say 4, less than delta, which remember is less than or equal to this, the delta 1 and the delta 2, the delta 1 used for the G and the delta 2 used for the F. We see that which is what we needed to show by the delta epsilon proof. So I hope what you got out of this is you got out of the fact that the triangle equality is important. And the key step was going from here to there. And then once we did this, once we added and subtracted the same thing and divided out, it was our mission to find a proper epsilon to use with this part that would cancel the size of G. And this is once you want this to cancel the size of F when you do that. And that's what this choice here was about. Now you could have just written this down and grind through the inequalities and you would be done. But, you know, and I guess I should say one other thing that maybe I wasn't too clear on. How did I know this right here? Well, remember if, let's say G minus big G is less than epsilon, then it's certainly, this means that like so. So then we could choose -1 for our epsilon. And then what that basically shows is that the absolute value of G is going to be less than or equal to the absolute value of G plus 1 by just adding G on both sides. Then take absolute values and you got it. So that's this little step right here. So thanks for listening. This is a little bit rough and dirty, but I think you can handle it.